example in a poem. The poem, the very famous poem that I wrote myself, like a big boy, says axis, plane, space. So that's the favorite, that's my multiple integration poem. So you got to say it like axis, plane, space, like you actually, are artistically singing this. What does that mean? It means when you have the latest integral here, so this one, you start with axis. The last integral to the left, that's only on an axis. So you look at x only on an axis. So x goes from 1 to 2 only on the axis. Then your second integral, that would be your plane. So now, when x goes from 1 to 2, y, how is y changing in your region? Now you draw an arrow in your region. Of course, the arrow is vertical if it's y changing, and the arrow is horizontal if it's x changing. So when my x is between 1 and 2, what's my y doing? My y is changing from this curve, which is y equals to 0, from this curve, which is y equals to 0, to this curve, which is y equals to pi. Now, of course, this is incredibly simple because all bounds are constants. So when all bounds are constants, and this is a very nice theorem, when all bounds are constant, we can simply, and that's a very, very, very important word, switch the bounds. So you can write this integral as the integral from 0 to pi, the integral from 1 to 2, x sine y dx dy. There's no problem. This is the same thing as this because the bounds are constant. Of course, it's extremely rare that you get bounds that are constant in Cartesian. Usually we get constant bounds a lot when we work with polar or cylindrical coordinates. And right, how do we evaluate this? Well, we just evaluate it now. So we're taking, let's say we want to evaluate this. So you're integrating x dx. Remember the invisible parentheses that we have here. So this is the integral of x dx. So the 0 to pi stays. So this would be x squared over 2 sine y from 1 to 2. And then this is dy, right? So this and this, they just wait for their turn. I do the inside integral. So this is going to be the integral from 0 to pi. When x is 2, that's 4 over 2. That's 2 sine y minus a half sine y. And this becomes the integral from 0 to pi of 3 over 2 sine y. And this is an integral that is extremely simple. This is minus 3 over 2 cosine y from 0 to pi, which is when you put in pi, this is going to be 3 over 2 minus minus becomes plus. When you put in 0, it's going to be 3 over 2. So the answer is 3. So again, the integration part, like starting from, let's say, here to here, some of the times, in fact, like at least 50% of the time, I'm just going to say dot, dot, dot. So when we reach this stage, I assume that you guys know how to integrate sine x and like cos x and x. Like these are simple integrals. So to save time, I'm going to sometimes, like at least 50% of the time, I'm just going to say dot, 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 right? So we've reached this integral. Now you know how to finish it. Right? So the general form of a double integral would be the double integral over a region R of some function f x y dA, where this is the region in the xy plane that defines the bounds. So this is the region in xy plane that's going to give us the bounds. This is what f of xy is, what we're integrating. and dA is either dy dx or the dx dy or dy dx, depending on which one do you want to take first. Right? So which one do you want to integrate first? Sometimes it doesn't matter, but sometimes it matters quite a huge deal which one you integrate first. All right, so let's consider our first double integral. And this, like series, takes practice. So let's say you want to integrate the double integral over a region R of y dA. And R is basically the triangle that has vertices 0, 2, 1, 1, and then 3, 2. Okay, so let's draw R. Zero, 2 is here. 1, 1, I'm going to say it's here. And 3, 2, 1, 2, 3, let's say this is 3, 2. So this is my region R. So this is R. Now remember my famous poem. Axis, plane. There's no space here because it's not a triple integral. So axis, plane. Okay. Which one do you want to consider only on the axis, and which one do you want to vary? Now, the equation of this line, this is a high school problem, right? If we find the slope, y equals y2 over y1 over x2 minus 1, y equals a half x plus a half. And the equation of this line is y is equal to y2 minus y1 over x2 minus x1 minus x plus 2. So, do you want to fix x, meaning fix x, by the way, let me say this once and for all. Remember the famous poem that I said, that you first look on the axis, then you look in the plane, then you look in space. Well, here we don't have space, so it's just axis and plane. The variable that you look on only the axis must have constant bounds. And this one will be leftmost, meaning the last one to integrate. So the order of integration would be like this. This would be the order of integration. Actually, writing it. So this is the order of integration. So when I say which variable do you want to fix, I mean which variable do you want to look only at the x-axis? And let me start by saying most students have a thing where they want to just fix x. So they start by fixing x. Let's see if that's a good idea on here. So if we fix x, remember, what does it mean fix x? Meaning we look at x only on the x-axis. So in your region, where is x on your x-axis? Anybody wants to tell me? What is the range for x only on the x-axis? My region covers which parts of the x-axis? Okay, you really don't want to talk to me. That's fine. So it covers 0 to 3. Right, on the x-axis, my region goes from here to here. Thank you, Mustafa. So now that's my axis. I've given my x my constant bounds. Now, how does my y change? So y changes vertically, right, along with the y-axis. How is y changing? Well, here it's changing from this function to this function. But then after this point, after 1, this is x equals to 1, it's changing from this function to this function. So it's changing function. So x from 0 to 3 doesn't work for me. So I need to say when x goes from 0 to 1, so now we're doing this first part here, then y is going from this curve to this curve. Look at the arrow. It's going from minus x plus 2 till y equals to 2. But then when x is from 1 to 3, so now I'm on the second half of this, right? From here to here, this part is this part, this part is this part. Now, y goes from this function, which is a different function than the other one, goes from minus a half, actually it's not minus, it's 1/2 x plus a half all till 2. So if I wanted to write this, this would be 2 double integrals. So if I wanted to evaluate this, I would write it as the integral from 0 to 1, the integral from minus x plus 2 till 2 of y, this is dy dx, plus the integral from 1 to 3, the integral from a half x plus a half till 2 of y dy dx. And you evaluate that. Now that's double the work, right? So what happens if I decide to fix y? See, again, when x gets constant bounds, we call this, we just fix x. Meaning x is the leftmost integral and it always has constant bounds. So how about you look at this and you fix y for me? So tell me, what is the range for y? Remember, axis, plane. So first on the y-axis, I'm fixing y. So I'm looking only on the y-axis, only on the y-axis. What does my region cover in terms of only on the y-axis? Y on the y-axis, Mustafa. Only look on the y-axis. Only look on the y-axis. Only look here. And tell me what parts of the y-axis does my region cover? It's very, very important. When you fix a variable, you only look on the axis. You don't bother looking anywhere else. So here's my region. I'm looking at, I want to fix y. I want to give my y the constant bounds. So where does my region cover on the y-axis? Hey, Johnny, I didn't see you come in. So exactly, it covers from 1 to 2. So on the y-axis, my region goes from y equals to 1 till y equals to 2. Now, vary x. So now x, so this is the axis. Now this is the plane. Now we need to vary x. What is x doing? Now in my region, make x change. Of course, you can draw anywhere in your region. It would still go from the same function to the same function. So in my region, what is x doing? X is going from this curve, the purple curve, to the blue curve. Anywhere in the region, look, it doesn't matter where you draw the arrow. It's going from the purple curve to the blue curve. I draw it in green. So what is the purple curve? That's x is equal to 2 minus y. So from 2 minus y to what's this? This is x is equal to 2y minus 1 to 2y minus 1. Of course, the bounds can't be x. It's x that you're bounding, so it has to be in terms of y. So the double integral will be the integral from 1 to 2 for y, the integral from 2 minus y to 2y minus 1 of y dx dy. So that's the double integral over the region R of y dx. Do we get this? And of course, to evaluate this, we can start by integrating y with respect to x, which is yx. And then the bounds are 2 minus y to 2y minus 1 dy. So this would be the integral. Let's plug in the bounds, 1 to 2. Y times 2y minus 1 minus y times 2 minus y all dy. So this is the integral from 1 to 2. 2y squared plus y squared is 3y squared. Minus y minus 2y is minus 3y dy. And so this would be y cubed minus 3y2 over 2 from 1 to 2 dot. Do you guys get this? I get nervous when people just don't talk. I don't know if you're not understanding anything at all, or you're understanding everything, or it's somewhere in the middle and you just took a vow of silence. Okay, here's a question from 2019. Evaluate the double integral over the region R of x dA, where R is the region bounded by BDD, that's bounded by y equals to x minus 2, and then y equals to 4 plus x. Of course, this one is a parabola. So let's see. People ask, do I have to draw the region? And I mean, yeah, you kind of do. How are you going to find the session if you're not going to draw the region? So let's see. How are you going to find the bounds? So this is a parabola, smiling parabola, which is because it's basically x squared minus 2x. But the form x minus 2 is nice because we know that 0, when x is equal to 0, y is equal to 0. And when x is equal to 2, y is equal to 0. So we know it looks like a parabola like this. And y equals to 4 plus x. 4 plus x, let's say it's when x is equal to 0, y is equal to 4. So let's assume this is 4, and this is y equals to 4 plus x. So R is the region bounded by these, so this is my region R. As I said, I hope many times already, multiple integration is about finding the domain of integration. Really, integrating is not the issue. Integrating is simple. So we want to find the domain of integration. So I want to ask you this. Do you want to fix your x or do you want to fix your y? Again, what does it mean fix my x? So do I look on the x-axis only, then I vary my y? Or do I look at the y-axis only and then vary my x? Look at this and tell me, please. So let's say we, well, you have to look at your domain, Harry, right? So you have to practice a few questions and then you'll see. Let's say I'm going to do what Mustafa is saying. I'm going to fix my y. Well, let's say you fixed your y. Let's say for by some, like, you found what this is. So let's say this is whatever it is. Let's say this is A, and let's say this is B, right? So let's say I did what Mustaf is saying, and you really have to try these things because you really have to practice this, right? So let's say y is between these two values. Great. Now let me vary my x. Vary my x means I'm gonna just draw x in my region. So here, x goes from this function to this function. Perfect. But what if you draw the arrow here? That's a huge problem here. Because x is going from the function to itself. So does that mean x is not changing? Look here, when you vary your x in this part of the region, it's going from this function to itself. Right? So fixing y is a terrible idea in this case. So let's fix x and vary y. Let's fix x and vary y. So where does my x live on the x-axis? So I gotta find what this value is, and I gotta find what this value is, but that's not a problem. Those values we can find using intersection. So x is from here to here. Now vary your y. Vary your y in the region. Look, anywhere you draw it, it's going from this function to this function. Draw a few of them. Anywhere you draw your vertical line, it's going from the parabola to the line. Are you seeing this? If you're not seeing this, you're going to have a huge problem with multiple integration. So please ask me. Anything is unclear, ask me, because this is the basis of what we're going to build everything on. If this is not clear, then nothing else will be clear. Do we understand how when x lives in the interval from here to here, we're going to find what those numbers are. That's not a problem. When we vary our y, anywhere you want in the region, y is going from this function to this function. Anywhere you want in the region. So if I want to find those intersection points, basically I have to find what's the intersection here and the intersection here. And you know how to find intersections. You set them equal. So x minus 2 is equal to 4 plus x. So x squared minus 2x equals to 4 plus x. So x squared minus 3x minus 4 equals to 0, which you can factor into x minus 4, x plus 1 equals to 0. So either x is equal to 4 or x is equal to minus 1. So this goes from minus 1 to 4. So on the x-axis, x goes from minus 1 to 4. What is y doing? Y goes from the parabola to the line. So my integral is the integral from minus 1 to 4, the integral from x squared minus 2x to 4 plus x dy dx. So when you start integrating, and I won't finish this, the integral of x is xy from x squared minus 2x to 4 plus x. So this is the integral from minus 1 to 4 of x times 4 plus x minus x times x squared minus 2x. And I am sure that you can finish this integral. Guys, do you get this? Do you not get this? Do you have a question? Do you not have a question? Anything? All right, well, thank you, Harry, for letting me know. I truly appreciate it. Okay, let's talk about the first application of multiple integrals. So area using double integrals. How do we find the area using double integral? How do you determine which equation is what bound? Johnny, good question. It's going from this one. Yeah, I'll highlight it. It's going from this. Oh, that's a bad highlighting option. From this one. Right? Do you see me highlighting this? What's this one? This one is the y equals to x minus 2, right? To this one, which is y equals to 4 plus x. So it's going like y changes that way, right? So it's going from this, the bottom part of this, and the upper part is this for every arrow. Better? Okay, so let's see. John, you will let me know if that wasn't clear, right? So how do we find area using double integral? So the area of R is equal to the double integral over the region R of 1 dA. When you take the double integral of 1, that gives you the area of the region that you are integrating by. Integrating over. So when you find the double integral of 1, that gives you the area of the region you're integrating over. So in 2018, here's what they asked them. They said, find the area. So find the area between y equals to 2x 4 minus x and y equals to x cubed using double integral. So, well, again, you ask, do I need to draw? Well, yes, you need to draw. How else are you going to figure out what's happening? Again, the graph isn't as bad as we think it is because this is x cubed. Everybody, I hope, knows what y equals to x cubed looks like. And y equals to 2 times 4 minus x, it's 0 when x is 0. It's 0 when x is 4. And it's a sad face parabola because it's 8x minus 2x squared. Because there's a minus 2x squared, the coefficient of x squared is negative. It's a sad face parabola. So I'm going to just exaggerate and draw it like this. Yes, I wanted it to pass by the points. You know what? I'm not making it nice anymore. Well, so this is the area between them. We have an area here, and we have an area here. They clearly meet at 0, but we need to figure out where do they meet here, and where do they meet here. Okay. I want you to think about this. The area, we all know that the area is the double integral over in the region R of 1 dA. So the question isn't the integral. The question is the bounds. If the yellow is the region R, and it's not difficult finding intersections, you just set this equal to this. This is not really a difficult thing. Do you want to fix your X and vary your Y, or do you want to fix your Y and vary your X? In this question, there's one way that's doable and one way that's terrible. And I think they did ask on that final to do it both ways, the terrible way and the easy way. So let me see if the 18 exam is here. Find an equation, differentiable, no. Here we go. Use dy dx and then use dx dy. So see, this is it. It was 8 points on 2018. And they did ask them to use both ways. So I'm going to show you how to use both ways. The other way is very difficult. It's annoying. So look, the easiest way to do this is to fix your X. So you fix your X from here to here. And then you vary your Y. So Y goes from here to here. And then from here to here. So it changes a little after 0 and before 0. So first you find your intersection points. 2x times 4 minus x is equal to x cubed. So 8x minus 2x squared is equal to x cubed. So x cubed plus 2x squared minus 8x equals to 0. So I factor out an x. That gives me x squared plus 2x minus 8 equals to 0. So factor out an x. X plus 4x minus 2 equals to 0. So either x is equal to 0, or x is equal to minus 4, or x is equal to 2. So this is the 2. Those ticks are not very accurate. So this is the point 2. This is the point minus 4, and this is the point 0. Now, please, how do I write this? If I just fix my x. So first of all, I'm going to say when x is from minus 4 to 0, y goes from this, which is the cube. So from this to this. Oh wait, that's not the cube. The other one is the cube. Oh, I destroyed it. So x goes from this, which is 2x times 4 minus x, to this, which is the cube. And then when x goes from 0 till 2, y goes from the green, which is the, y goes from x cubed to the purple one, which is 2x 4 minus x. Look at the region and tell me if you see it. So this is the integral from minus 4 to 0, the integral from 8x minus 2x squared to x cubed 1 dy dx, plus the integral from 0 to 2, the integral from x cubed to 2x 4 minus x 1 dy dx. Do you get this? Okay. The problem is that in the question they said write it as dx dy. That's a problem. Look, I'll tell you why it's a very, very simple problem, and then you can agree with me or not agree with me as you wish. So this is x cubed. So this is y equals to x cubed, or we can write it x is equal to y to the 1/3, no problem. And this is the other one. So it's gonna meet here and then it's gonna go like this and come down like this. Not a problem. So here's my region. I know that this point is -4, not that I need it right now. So, but if this point is -4, if I put -4 into x cube, or so if x is equal to -4, y is equal to -64. And this is y equals to 0 where they meet. Now we need to figure out what this point is. And that's the first problem. Actually, it's not a big problem because, hold on, the x cube does this. No, you don't. They actually asked for it. They asked. So they are being very mean about this. Look. So when x is equal to 2, the intersection point 2, that's if x is equal to 2, then y is equal to 8. So we're going, the first issue is where does y live? So y goes from -64 to 0, and then from 0 to 8. It's not so difficult. Look, when you change x, it's going to go from this curve to this curve here, and from this curve to this curve here. So far, you haven't seen where the difficulty is, correct? So if y goes from -64 to 0, so we're here, from -64 to 0, x goes from the purple curve, and the purple curve is x is equal to y to the 1/3. And here is where you realize you have a big issue. To the green curve, and the green curve is y equals to 2x minus 8x minus 2x squared. So how do you find x? You see the problem? So how do you find x? And then if you go y from 0 to 8, then x goes from, again, that which we don't know, to y to the 1/3. Because that part we know. It's that part that we don't know, the green part of this curve. Ready for this? How am I going to find the equation of the green curve? And don't be shocked, we're going to use the quadratic formula. So minus 2x squared plus 8x minus y equals to 0, right? I'm solving for x. So x is equal to minus b plus or minus the square root of b squared minus 4 times a times c, so minus 8y, all divided by minus 2a. So if I write this as plus and minus, so this would be minus 8 minus root 64 minus 8y all over minus 4. You know, let's just agree that we can make all of them plus. and then minus 8 plus root 64 minus 8y, all divided by 2n. So if you want, you can make this a plus, this a minus, and this a plus. So which one is it? Which one is it? And the idea is that it's the one that has the minus, because every parabola would be broken up into two pieces, where on the left would be the smaller x, and on the right would be the larger x. Now, please note that this would be the larger x, and this would be the smaller x. Right? Because here you're minusing something, here you're adding something, here you're minusing something. So since we're on the left side of this parabola, so that is the equation that you are looking for right here and right here. Don't hate me for it, guys. It was a question on one of your finals. And I figured I should show this to you because just in case it gets asked again, so you know what to do. So how do you find the equations of the branches of a parabola? Well, you simply use the quadratic formula, and the minus is the smaller branch and the positive is the bigger branch. Do we get this? Everything in this problem is typical except finding the equation of the green curve. Like varying x is not a problem. You know there are two regions, varying y. Everything is okay except the part where you have to solve for x using a quadratic formula with a y in it. All right? Okay, so now let's start by doing other stuff. The next order of business is switching bounds. And I should say that Queens is very big on switching bounds. Like I've seen this come on many finals. So changing the bounds of integration. Now, sometimes they tell you, sometimes they don't tell you. So let's just pick up like a random test, a random final. So pick one. 2022, because we haven't done 2022. Switching bounds. See, this is polar. I have prepared questions from other tests. It's not that I didn't prepare, but I just wanted to look at this. This doesn't have changing bounds. Oh. Center of mass, yeah, this doesn't have changing of bounds. So let's look at the ones that have changing of bounds. Shall we try 2021? If I don't find, those are the only two exams I left without actually dissecting them for questions. I figured we could do some of them in class. Here we go. See, I told you we will find a changing of bounds question. It's impossible to go 2-3 exams without finding one. This is a very popular topic. So this is from 2021, and I'll explain to you fully how do you change bounds of it. So calculate the iterated integral. So if you want to calculate this, I'm not gonna calculate it. I'm just gonna show you what to do. So you're taking the integral of 1 dx, right? So the integral of 1 dx is just x from y squared minus 1 to 2y minus 1. I find these lines very annoying, so allow me to just erase them, because we know that these are the bounds for x, like we're not, right? So this would be the integral from 0 to 2 of 2y minus 1 minus y squared minus 1. I said I won't do it, but I'm going to do it. The integral from 0 to 2. So this is 2y minus y squared dy. So this is y squared minus y3 over 3 from 0 to 2. So this would be 4 minus 8 over 3, which would be 4 over 3. You should practice a few of those to make sure you're like handy in changing the bounds, handy in writing the everything. So how do we interchange bounds? And here we're doing it because they asked us to. I'm going to show you an example after this where we're doing it because we have to. So to interchange bounds, to switch the bounds of integration, the method is this. We write the old bound. We draw the region. Unfortunately, you have to draw, and then you write the new bounds. So, what are the old bounds? X is between y squared minus 1 and 2y minus 1 when y is between 0 and 2. I cannot stress how important it is to know how to read bounds and know how to graph bounds. So let's do this. X is equal to y squared minus 1. So how do we graph x is equal to y squared minus 1? So x is equal to y squared, that would be this. But then minus 1, we bring it back 1 till here. Of course, you can just give y values. If y is 0, x is minus 1. And if y is 1 or minus 1, x is 0. So you know that this is a parabola that looks like this. Now, please note that you're only interested y from 0 to 2. So technically, you don't care about this part, right? Technically, you don't care about this part because you're only doing this for for y from 0 to 2. So you're only interested when y goes from 0 till 2. So you're only interested in this range for y. So this part is really, options, right? And then what is x is equal to 2y minus 1? So if y is 0, x is minus 1, so they meet here. And if y is equal to 1/2, y is equal to 1. Sorry, if y is equal to 0, x is equal to minus 1. So this is minus 1, 0. And then if y is equal to 1, x is equal to 2. So 1, 2. If x is equal to 1, or y is equal to 1. I don't know why I'm drawing a blank here. If y is equal to 2, let's just put y equals to 2, the upper bound. If y is equal to 2, then x is equal to 3. So dot, 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 dot. So this is, they're going to meet when y is equal to 2. We're going to bring this back down, and it would be x equals to 3. And that's the graph. Please note that when y goes from 0 to 2, when we are on y 0 to 2, what is x doing? X is going from the parabola to the line. So look, from the parabola to the line, from the parabola to the line. That's how I know that this is my area. From the parabola to the line. Do we see this? Okay, now I want to change my bound. So now I'm going to look at x. What is the range for x? I'm fixing my x. And what is y doing? So give me the range for x, please. What's the range for x? So x goes from -1 to 3. That's very good. So x lives on the x-axis from here to here. What is y doing? Remember, y varies with the y-axis. What is y doing? Y is going from the line to the parabola. Now, here, if x is equal to 2y minus 1, that means y is equal to x plus 1 over 2. So it goes from the line to the parabola, where here we have y squared is equal to x plus 1. So y equals, technically you should say plus or minus, but we don't need plus or minus here because y is positive. We're taking the upper branch of the parabola. So this is the square root of x plus 1. So this is the integral from -1 to 3, the integral of 1/2 x plus 1 to the square root of x plus 1. What was it? 1? Yeah, just 1 dy dx. Calculate bounded by the y-axis. Okay, so this one is polar. We're going to do it when we get to polar. And this part is independent of a and b, so it has nothing to do with a and b. Do we get this? Okay, now I'm going to ask you another question of changing the bounds. So I'm going to be honest with you. I don't know. Are you following? Are you not following? Is this too fast? Is this too slow? Everything's okay? I'm not sure. So evaluate the integral from 0 to 3, the integral from y squared to 9 of y cosine of x squared dx dy. And I'm not saying switch the bounds, but you will see that you will need to switch the bounds. I want you to tell me why. So take a second and tell me why. Well, let's say you don't want to change the bounds. Let's say you don't want to change the bounds. Can you integrate cosine x squared dx? Think about it, guys. Let's say you don't want to switch the bounds. Would you be able to integrate cosine of x squared dx? That's not something that we can integrate. To integrate cosine of x squared, we would need some kind of like x cosine of x squared or 2x cosine of x squared. So we are able to use substitution. So I cannot. What's the integral of cosine of x squared dx? We don't know. So it's not something that we can integrate automatically like this. While if it was the integral of cosine x squared dy, that would be no problem. It would be y times cosine of x squared. Do you understand what I'm saying? If this was a dy, then this would be just a constant. So the integral of cosine x squared will be very simple. I am able to integrate cosine of x squared dy, but I'm not able to integrate cosine of x squared dx. Can I get an okay for this? So we have to change the bounds. So how do we change the bounds? We write the old bounds, we draw the bound, we draw the region, and then we write the new bound. So here, y is between 0 and 3. X is between y squared, and 9. Can I give you 30 seconds to try this? Come on, 30 seconds. Try and draw this for me. So x is equal to y squared is this. Of course, again, there is this, but I'm only interested in y 0 to 3. X is equal to 9 is this. Well, if x is equal to 9, then y is going to be equal to 3. Regions are always well drawn, so like you're not going to find y equals to 3 like at a completely random location. So where is my region? Is it 1 or 2? So when y goes from 1 to 3, when y goes, from 0 to 3, x goes from y squared to 9. X goes from y squared to 9. And well said, Musdaf, this would be my region. Now I want to switch the bounds. Now I want to fix my x and vary my y. So fix your x. What's the range for x? So on the x-axis, x goes from 0 to 9. Y goes from 0, this is y equals to 0, to y equals to root x. This is y equals to root x. So the integral is the integral from 0 to 9, the integral from 0 to root x of y cosine of x squared dy dx. And you can see that now this is something that you could totally evaluate. Because the integral of y dy is y squared over 2. And then this is just cosine of x squared, which is a constant with respect to y, from 0 to root x dx. When you plug in root x for this, let's put the half on the outside. Y squared, if y is root x, then that's x cosine x squared minus 0. So that's just x cosine of x squared. And you know that you can now integrate x cosine of x squared, right? So you can take u equals to x squared, du is going to be 2x dx. So this would be the integral of 1/2 cos u, which is sine u. So this would be 1 over 4 sine x squared from 0 to 9. And then that would be 1 over 4 sine 81. Right, if you forgot substitution, I can do this in a bit more detail. So if u equals to x squared, du is 2x dx. So the integral becomes 1/2 x cosine u, and then dx is du over 2x. So the x and the x cancels. That on the outside becomes 1 over 4. And the integral of cos u, that's sine u. And then when you bring back the u to what it was, so it's 1 over 4 sine x squared. Of course, I'm not saying plus c here because there's bounds here, and I'm going to use it for the bounds. Do you get this? Okay, here's an example. I'm gonna make this a little bit harder now. So here's an example that's a little bit harder. So you have write the integral from 0 to 2, the integral from 0 to 6x. Mustaf, don't be sorry at all. There's that 1/2 right here. And there's that over 2 right here. Right? Because if you solve for dx is du over 2x. So there's that 2 that multiplies by the 1/2 right here. Make sense? Thank you for asking. Always, 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 thank you for asking. When you ask, you make the session better. That's the rule. So change this. To this. So they're asking you for the bounds. So change this to a dx dy integral. Well, long story short, you got to draw the bounds. So here, if x is from 0 to 2, y is from 0 to 6x. And if x is from 2 to 4, then y is from 0 to 16 minus x squared. So we got to draw these. And I want you to know that I'm trying to go as slow as possible. In fact, we are a little bit behind schedule. So we're a little bit, not a lot, I'm not worried about time, but we're a little bit behind schedule because I'm trying to do more examples. I'm trying to do them as slow as possible. So if there's still anything that's not clear, please ask me. Please just say something like explain this, do that. I don't get this, change that. Right, so when x is from 0 to 2, so from 0 to 2, y is from 0 to 6x, so this is y equals to 6x. So when x is from 0 to 2, so y is equal to, y is from 0 to 6x. I want to point out that if x is equal to 2, y is equal to 12. Wait. Yeah, but then I need to push this down again. Now, so where is my region? My region is here. When x is from 0 to 2, y is from 0 to 6x. Nice enough region? I think so. Now, when y is from 2 to 4, sorry, when x is from 2 to 4, y is from 0 to 16 minus x squared. 16 minus x squared, ladies and gentlemen, starts at 16 and it goes like this. I gotta make it artistic to make it like this. Here we go. It's a parabola, right? 16 minus x squared is a parabola. It's 16 when x is 0. And then when x is equal to 2, you're going to get 12. So it matches this. And then when x is equal to 4 is 0. So from 2 to 4, y goes from 0 to 16 minus x squared. See how nice it is? It gave you one solid region. So now I need a range where y is fixed, because dx dy, and then x varies from a function to a function. Don't forget that this is y equals to 16 minus x. All right, seriously now, I need you to do this on your own. If you can't do this, it means there is something fundamental that you have not understood and you really should ask me. And if you don't ask me, I will have no way of knowing that you don't know it. Because very, very soon I need to move to polar coordinates. We're going to take a break. Then I'm going to go to polar. And after polar, we're going to go to triple integrals. We're going to do like a lot more difficult stuff. I just need to make sure that we're okay up to this point. So take a minute and please write this. Now fix your y for me. Fix y, vary x for me. Will you be able to find the bounds? And if you do, then good for you. You're on the right track. So where does my y live? My y lives from 0 to 12 because my region covers y from 0 to 12. So y goes from 0 to 12. Where does my x vary? X varies from this line, which is y over 6, to this line, where x squared is equal to 16 minus y. So x is equal to the root of 16 minus y. I don't need to say plus or minus because I'm in the region of positive x. So to the root of 16 minus y. So the new bounds on this integral are going to be 0 to 2 for y, y over 6 to the square root of 16 minus y, f of xy, dx dy. 0 to 12, sorry. I wrote 12 and I wrote 0 to 2. Thank you, Harry. Ta-da! Right, so two comments before we take a break, before we go to polar also. Don't forget that the area using double integral is given to us as a equals to the double integral over the region R of 1 dA. So this is the area. So the area R is, if you want to find the area R, take the double integral of 1 dA. For example, and by the way, if you want to find the mass, so let's start learning new constant. If you find the mass, if you want to find the mass of a region using double integral, then the mass is equal to the mass, of course, of a region R. Then to find the area, you take the double integral of 1. To find the mass, you take the double integral of the density, dN. Right? To find the area, so isn't mass area times density? And if the density is variable, so technically you're multiplying by the density to get the mass, but since density is variable, it goes inside the integral. So the area is the double integral of 1. The mass is the double integral of density dA. And just to show you how like this is nice, let's say somebody tells you evaluate the integral from 0 to 3, the integral from 0 to 3 minus x of 5 dy dx. And let's say evaluate using areas. So we don't want you to evaluate it using integrals. We just want you to find using areas. So what is this? Anytime the inside of the integral is a constant, you should think of area or volume. So this is 5 times the double integral of some region R of 1 dA, correct? This is dA. You move the 5 outside. So this is 5 times the area R. Now, what is the area R? That's really not so hard if you think about it. X is between 0 and 3, and Y is between 0 and 3 minus X. So X goes from 0 to 3. Y goes from 0 to 3 minus X. This is the line 3 minus X. So this is R. You are telling me that we don't know the area of R? Right? So the area of R is a half times base times height. So this is 945 over 3. Right? Why am I saying this? Anytime we have the double integral over region R of a constant dA, then this would be K times the area of R. Now, sometimes we don't know the area of R. Sometimes we have to do the computations, and that's fine. But if we know the area of R, then that would be great, because this would be a huge shortcut and it will save us a lot of time. Do we get double integrals as a basic? Now we're gonna learn new types of bounds. We're gonna learn polar coordinates. And once we learn polar coordinates, we are like one step closer to knowing all types of integration. We still have to do the triple integral bit, but polar coordinates take us one step closer to more interesting regions. Of course, we're going to start with easy polar, and then we're going to make it more and more different. Questions for me? Right now it is 6:48. Are we okay doing like yesterday and taking just 15 minutes for our first break? So if we are okay with time, we can add the 5 minutes to the next break. If we're not okay for time, then we save those 5 minutes and we solve extra problems. So let's be back at 7:03. I just need to ask you for a small, very, very small favor. Please, 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 can you take a second and fill the evaluations? The link is in the chat. If you open the chat, you'll see a link. Click on that link. Please, please, please do the evals. Usually people who think I'm terrible will run and will do them, and people who think the session is good, or hopefully better than good. But anyway, they won't, because they assume everybody else is saying the same. Please, good or bad, hopefully good. Please, please just take a moment to let me know how the session is going. I appreciate it. Right, so polar coordinates, and wow, it's now 6:49. So let's start the 15 minutes now, so you don't lose a minute of break, and you do the evaluations. Thank you very much, and see you in just a bit. We're back. So I hope you took a moment to fill the evaluations. Let's now discuss polar coordinates. So these are extremely useful coordinates when the region in the plane is a circle or a disk or parts of a disk. Now, how does polar coordinates look like? Instead of, and I'm sure you've seen this before, I'm sure this is not the first time you're working with polar coordinates, you've at least solved one question on an assignment somewhere. So instead of working with X and Y, so a point in the plane, instead of saying it has component X, excuse me, and component Y, so we're going to say that the component of this is r and theta. So the component of this point, the coordinates of this point, I'm sorry, is r theta, where r is the distance from the origin to the point. So theoretically, r bigger than or equal to 0 all the time. Please be careful to what I'm just saying right now. R always starts at the origin and goes through till we reach the point. And theta starts here. Theta starts at the positive z-axis or the positive x-axis. Its positive rotation is counterclockwise as you would expect it to be, and that is the angle theta. So this point would be at angle theta and a distance r from the origin. Now, through basic geometry, x is equal to r cos theta. You can see that. So r cos theta would give you this distance x. R y is equal to r sine theta. So this is how we switch from polar to Cartesian. From Cartesian to polar by changing x to r cos theta, y to r sine theta. Please note that dx dy is r dr d theta. Whenever we're finding dx dy and we're changing it to polar, we write the dx dy as r dr d theta. R is called the Jacobian. You don't really need to know why for now. Now, also with geometry, because this distance is y right here, and this distance is x. So basically, x squared plus y squared is equal to r squared. Some people prefer to say r is equal to the square root of x squared plus y squared. That's also fine. Right, and if you want to find theta, right, this is theta. So you can see that tangent theta is y over x. So if you want to solve for theta, theta is equal to tangent inverse y over x. Although really this is used, but not as used as, not as much as finding r. Okay, let me right away give you an example where polar coordinates are essential and Cartesian coordinates are useless. So let's say r is the region to the left of the y-axis between circles of radius 1 and 2. So R is our region between, to the left of the y-axis, between the circle of radius 1 and the circle of radius 2. That's my region R. Now I invite you, could you think of a way to write this in Cartesian? There's really no way. How are we going to write this in Cartesian? It's terrible. Right, so here, this is on top of this, and this is on top of this. Those are on top of each other. I'm looking here, like the region goes from here to this, but then here, from here to here. Like it's a terrible idea to write the bounds of this region in Cartesian. But in polar, It's no problem at all. So how are we doing this in polar? We start at theta is equal to pi over 2, and we go all the way till theta is equal to 3 pi over 2. So my region falls between the theta pi over 2 and then the theta 3 pi over 2. And then how do I find my r? Please remember, I'll always start at the origin and it goes through your region. Now, anywhere you draw r in your region, anywhere you draw it, it's going from this to this. So from r equals to 1, circle of radius 1, to circle of radius 2, so r equals to 2. Of course, if we have a circle, and I'm going to write this right now. So if we wanted to do this in polar, this is very simple. These are the bounds in polar. Now, to make this even more clear, I want to discuss with you what are some nice curves with polar. So I'm going to discuss with you some nice curves with polar. So curves where the polar is so much easier to work with. So when we have r is equal to k, what's the curve r is equal to k? R is equal to k, that is the circle with center 0, 0, and radius k. Here, this is r is equal to 1. This is r is equal to 2. Now, what happens if theta equals to a constant? Theta equals to a constant, that's a straight line through the origin. Right? With slope tangent theta. Think about it. If you have theta equals to a constant, this is theta equals to a constant. Theoretically, this is theta equals to a constant. Like it's the same theta. So if this is theta, any point on this line would have this as x, this as y. So tangent theta is y over x. So y is equal to tangent theta times x. So the slope of the line is tangent theta. Let me give you an example. So if somebody tells you the line y equals to x, how do you put this in polar? What's the line y equals to x in polar? Well, if y is equal to x, that means tangent theta is 1. That means it's theta equals to pi over 4. And you can even see it when you draw the line. Y equals to x is this line. So it's sort of the middle angle, right? So this is theta is equal to pi over 4, or y equals to x. Again, how do I get pi over 4 if I'm calculating things? Tangent theta is y over x. Tangent theta is y over x. And since y is equal to x, then tangent theta is 1. That means theta is pi over 4. Okay, let's make the curves a little bit more difficult. What is the curve in polar? R is equal to k times cosine theta. What's the curve? R is equal to k cosine theta. This is a circle with center center k over 2, 0, and radius k over 2. Believe me when I say you might need this. Let me show you why. So if you want to see it on a graph, let's do it. This is the circle of center k over 2 and of radius k over 2. how can I parameterize? So how can I write the bounds? If we're talking about this region R, then how can I write the bounds for this R? If R is this region, then how do I write the bounds for R? What is theta and what is R? Excuse me. So if this is the region that we're trying to write in polar, then what is theta and what is R? Well, theta goes from minus pi over 2 to pi over 2. What are the bounds for R? Apparently, I'm allergic to this curve. Excuse me. So, what's R doing? R starts at the origin, and anywhere you draw it, it goes to this curve. So R starts at the origin, and it goes to the curve K cosine theta. If you need bounds like this, then this is how you do them. Okay, what's another nice polar curve? If it's R is equal to K sine theta. Now, if it's a sine theta, then this would be a circle with center 0 K over 2 and radius K over 2. So on a graph, this looks like this. So the center is on the y-axis and the radius is K. Okay, let me ask you this. Let's make this bigger. We're not. Sorry, I destroyed my own creation. So if this is my region R, how do I write the bounds for my region R? What is theta and what is R? If you need to write the bounds for a region R that looks like this, how would you find theta and R? Well, theta goes from 0 to pi. And in my region, R starts at 0 and it goes to the curve and it goes to the same curve every time. So R goes from 0 to K sine theta. Am I making sense? Is this clear in terms of polar? By the way, this curve, if you're looking at it in Cartesian, it would be x squared plus y squared is equal to kx. This is what it looks like in Cartesian. And this curve in Cartesian looks like x squared plus y squared is equal to ky. I can show you why. Say, for example, here, because x squared plus y squared is r squared, y is r sine theta, and then when you simplify by r, you get r is equal to k sine theta, which is what you have right now. Do you understand what I'm saying? So let me ask you this. I think this was on an assignment. What is the integral from 0 to pi over 2? The integral from 0 to 2 cos theta of r dr d theta using areas. Is this something you've seen on an assignment? Assignment 4, maybe? Maybe, maybe not. So how would you do this using area? Look, you guys, it all lies in the understanding of this. This is saying that theta is between 0 and pi over 2 when r is between 0 and 2 cos theta. Of course, r dr d theta, that's like saying dx dy or dA. So this is like 1 dA. So how do we draw this? What's r equals to 2 cos theta? R is equal to 2 cos theta is the circle centered at 1 and of radius 1. So this is r is equal to 2 cos theta. This is 1. But be careful, theta only goes from 0 to pi over 2. So when theta goes from 0 to pi over 2, r goes from 0 to the curve 2 cos theta. So this is my region R. So therefore, this is equal to, this is my region R. So this is equal to the area of R, which is half the disk. So 1/2 of pi r squared, which is pi over 2. Okay. Let me show you, unless of course you have questions. Here's an example of how polar coordinates can be also very useful. How would you evaluate the integral from 0 to 1, the integral from x to the square root of 2 minus x squared of x dy dx? Let's agree that if you were doing this in Cartesian, it would be very, very annoying. Right? I mean, you're going to get x, y, and then you're going to replace y by this minus y by this. So it's going to be very, very annoying. So how do you do this in polar? Of course, you can if you want. You can do this in Cartesian if you insist. I'm showing you how to do this in polar so you have both ways. So when x is between 0 and 1, y is between x and the square root of 2 minus x squared. Now I need to pause for a second. This curve is a very particular curve, so I'm going to include it here. This is a very special curve or a function. Y equals the square root of a squared minus x squared. Do you know what this curve is? Y equals to the square root of a squared minus x squared. That would be the semicircle with center 0, 0 and radius a. I'm going to show you why. Because square both sides, you're going to get y squared equals to a squared minus x squared. So you move the x squared to the other side, you get x squared plus y squared equals to a squared. Now, why is it the semicircle? Because y is positive here. Y equals to a square root, so y is positive. So this is this. So let me draw my region and we'll see how we could do this in polar. So when x goes from 0 to 1, y is between x, so this is y equals to x, and the square root of y equals square root of 2 minus x squared, so it's this disk of radius root 2. Let's make this one right here. Of course, when this is 1, they just meet. So when x goes from 0 to 1, y goes from x to root 2 minus x squared. So this is the region R that we're talking about. So this, as a note, y equals to the square root of 2 minus x squared. That's the circle of center 0, 0, and radius equal to root 2. So how can I do this in polar coordinates? Let me ask you, what is y equals to x in polar? We talked about this. What's y equals to x in polar? That would be theta equals to pi over 4. We did it a few questions ago. So how do I write my region in polar? Theta goes from pi over 4 to pi over 2. So this is theta goes from pi over 4 to pi over 2. R starts at the origin, goes through my region to the end of the region. So R goes from 0 to root 2. And what is x? X is r cos theta. And what's dy dx? It's r dr d theta. So the integral of r squared is r3 over 3 cos theta from 0 to root 2. So this would be 2 root 2 over 3 cos theta. The integral from pi over 4 to pi over 2. The integral of cos theta is sine theta from pi over 4 to pi over 2. Sine pi over 2 is 1. Sine pi over 4 is root 2 over 2. And that's the answer. So this is 2 root 2 over 3 minus, that's 2 divided by 2, 2 over 3. That, ladies and gentlemen, is an example of how we could use polar coordinates instead of Cartesian coordinates when the region is a disk or part of a disk. Right? So now we've been working using double integrals to find area, to find mass. Now I'm just going to give you like a whole list. So now we're going to I'm going to give you like a whole list of how do we use integrals to find what, and then after that it will just be practice, 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 practice. So I'm even going to do this on a, on a new page. So how do we find area